In today's video, we're going to look at the graphical interpretation of derivative. In your IB syllabus, this is SL 5.2 and SL 5.8. Although in 5.8, we're not going to deal with optimization in this video. That will be in a later video. In the graph y equals f of x, let's identify some key functions of this graph, starting with the domain. Okay, I could say that the domain of f of x is from A1 all the way to A7. Notice I'm using brackets because I'm including A1 and A7 as part of my domain. Okay, now the endpoints of this function occur at A of 1 and at x equals A of 7. So I notice that my graph begins and ends. Notice there's not an arrow on these graphs, so they're not continuing on. Now let's identify all the local maximum and minimums that we have in the graph. So we have a local max at these 3 points. Notice it can be in the inside of the graph or at an endpoint. So our local maximums occur at x equals A of 2, A of 4, and A of 7. Next, we'll identify where our graph has some local minimums or dips in the graph, smallest points of the graph in those points near it. So the endpoint A of 1 and these 2 points A of 3 and A of 5. To get collectively, local maximum and local minimum points can also be referred to as turning points. So there's a good vocabulary term. So sometimes the IB will ask you, find the turning points of f of x. And that means they are asking you to find all the local maximum and minimum values on the graph. Another term that you will sometimes see is the IB might ask you to find the extreme values of f of x. So extreme values, turning points, local max and mins are all the same thing. Notice that this highlighted point here is not a turning point. It is not a local max or min. So continuing our knowledge of what we know about this function. Now, next thing I'm going to look at is I'm going to look at the graph of f of x. I'm going to find all the intervals in which the graph is increasing. So therefore, we're increasing on the open interval from A1 to A2. And f of x is decreasing on the interval from A2 all the way down to A3. Then the graph starts increasing again until it gets to A4, so increasing on the interval from A3 to A4. Then the graph starts going down, so we're decreasing on the open interval from A4 to A5. Switching to increasing, and this time it increases all the way to the end of the graph. So from A5 to A7, our function is increasing. Okay, remember that has a positive gradient, means that the function is increasing, and if A has a negative gradient, that means the function is decreasing. So recall that derivative is equal to gradient. So another way that we could find where f of x is increasing, they might ask you, find where the derivative is greater than 0. And that answer would be the same. Intervals A1, A2, A3 to A4, and A5 to A7. Otherwise, you might be asked to find the intervals in which the derivative is less than 0. And that is the exact same answer as when the function f of x is decreasing. So I would look on my graph and find where my function decreasing or going down, and that's from A2 to A3 and A4 to A5. Remember, f of x is increasing is the same as asking for when the derivative is positive, and f of x is decreasing is the same as asking when the derivative is negative. This is an extremely crucial fact that you will need to use throughout our calculus unit, so please make sure you memorize this. Recall from earlier, turning points are where the local maximum or minimums occur on a graph, and algebraically you can find a turning point by setting the derivative equal to 0. Therefore, apart from your endpoints, which are also possible turning points, the candidate points for your turning points or your maximum minimum graphs on your graph are the following. Step 1, you're going to find the points where the derivative is equal to 0, and then step 2, you're going to find where the derivative does not exist. These points, possible turning points, are called stationary points. When a derivative equals 0, we have a horizontal line. So you can see at our local maximum and minimums here, if I sketch my derivative, which is our slope of our tangent line, we'll notice that our tangent lines are parallel. So all of these have derivative equal to 0. Now another possible turning point would be here, where our derivative is actually undefined. So I have marked all the stationary points on our graph. But notice that this last stationary point is not a turning point because it is not a local maximum minimum on our graph. In our first example, we're going to find the coordinates of the stationary points of y equals 2x cubed minus 15x squared plus 24x plus 3. So first thing I got to do is got to find the derivative of this function. So our derivative would be 6x squared plus 30x plus 24. Now I need to figure out when this derivative is equal to 0 and when this derivative is undefined. So I will start by setting the derivative equal to 0 and solving this quadratic. So when x is equal to 4 or when x is equal to 1, our derivative is equal to 0. Then I ask myself, when is this derivative undefined? Well, it's a quadratic, which is a parabola, and that exists for all values of x. So it's defined over all real numbers. So I do not have to test for when the derivative does not exist, because it always exists. So next, notice that the question asks to find the stationary points. So that means I need to find the y coordinates for each of these x values. So I'm going to start by plugging in x equals 1 into my original function, simplifying it down. And I find that y is equal to 19. Now I'm going to repeat this process, substituting in 4 in place of every x in my original function. And I find that y is equal to negative 8. So therefore, my stationary points of this function y is the point 1, 19, and the point 4, negative 8. We know how to identify stationary points. We need to figure out how to determine if those stationary points are local maximum or minimum. We have two methods of doing this. The first method is called the first derivative test. Now, in order to do the first derivative test, we're going to check the sign of f of x to verify if the function is increasing or decreasing just before and after our stationary point. So if the function is increasing and then decreasing, that stationary point will be called a maximum. If the function is decreasing and then increasing, the stationary point is called a minimum. 3 steps are the process you will take when you're asked to find the first derivative test. First, you find the first derivative. Then you set the first derivative equal to 0 or when it's undefined. And these will give you the roots of the function or when the function has a horizontal asymptote. Then we construct a table of values. And we use this table of values to classify our critical values. Our critical values are the A, B, and C listed above when we set the derivative equal to 0. Now, if I go from increasing to decreasing, I have a minimum value. If I go from decreasing to increasing, I have a maximum. And if the sign does not change, it is neither maximum nor minimum. So these are the 3 steps that you should follow anytime you're asked to find your maximum minimums of a function. So let's try an example. Okay, we're going to classify the turning points of the following function. So for step 1, find the derivative. Okay, differentiating f of x, I end up with x squared minus 4x plus 3. I'm going to set this derivative equal to 0 or when it's undefined. Now since it's a polynomial, it will never be undefined, so all I have to do is set it equal to 0. Solve the resulting equation. And I figured out that x equals 3 or x equals 1. These are my critical values. And these are where my possible turning points can occur. So now I need to set up my table of values in which I'm going to figure out the classification of these turning points. On the top of my table, I'm going to put my key values or my critical values here, so in increasing order, so that's going to be 1 and 3. Then I'm going to choose a value that's less than 1 and plug it into my derivative. I don't really care about what this value is. The key is that this needs to be either, I need to know if it's a positive or negative derivative. So plugging 0 into my derivative function, I get 3, which is a positive number. So I put a plus sign in that point in the table. Now I'm going to choose a number between 1 and 3, so I'll try 2. And I get a negative times a positive, which is equal to a negative. Now I'm going to try something greater than 3, so I'll do 4. Now notice it doesn't matter which form of the derivative you plug it into, you just plug it into one of those. So now I'm going to classify these turning points. So I notice I go from increasing to decreasing to increasing. So my first turning point must be a maximum, and my second turning point is a minimum. Conclusion, therefore, f of x has a local minimum at 1 comma. Now to find the y value, I go back to my original function, place 1 in place of every x, and to solve this equation. So therefore, my local maximum occurs at the point 1 comma 19/3. My local minimum would occur at 3 comma, and I repeat this process, replace every x with 3 in my original function. And I get the 0.35. And that is what you do in order to classify turning points using the first derivative test.